So good afternoon, everyone, and welcome back to this session, second session of the day of his GIAN course. So in this lecture today, Professor Tokonami sir will give his talk on dosimetry of radon isotopes. And so without much delay, I invite Professor Tokonami sir to start his talk.
Can you hear me?
Yes, sir. I can hear you,
Okay.
sir.
Can you see my slide?
Yes, sir. I can see your slide.
Okay, thank you. So now I'm deliver a lecture on dosimetry of radon isotopes. To start, we have to confirm the following findings. The direct contribution of radon gas to radiation exposure is relatively low. Short-lived decay products are the main contributors to the radiation exposure. The relation between the radon concentration and the corresponding concentration of radon progeny is expressed through the equilibrium factor. Radon is comparably easier to measure. Its concentration has been used as a surrogate for radon progeny concentration. However, as a majority of the radiation dose originates from radon progeny, caution is necessary when relying solely on radon concentration for dose assessment and control. The dose conversion factors are used to calculate doses from all radionuclides for purposes of radiological protection. Here's important information in ICRP publication 24, Radiation Protection in Uranium and Other Mines. ICRP's first recommendations specifically on radon were published in 1977, focusing on protection in uranium and other mines. It was noted that radium-226 is part of the uranium decay chain, which is found almost everywhere and hence not limited to uranium mines. Noting the rapid development of radon epidemiology, an annual limit on the exposure to radon progeny of 12 working radon months was recommended. ICRP publication 65, the protection against radon-222 at home and at work. In 1993, ICRP publication 65 established the use of action levels in terms of radon concentrations. The recommendations were updated and expanded to include protection at home. Assuming 7,000 hours per year indoors or 2,000 hours per year at work and an equilibrium factor of 0.4. Quantity. Nominal fatal and detriment coefficient at home and at work. Unit millijoule hour per cubic meter. Recommended value 8 times 10 to minus fifth. dose conversion convention, effective dose per unit exposure. At home, 1.4 millisievert per millijoule hour per cubic meter. Dose conversion factor, a dose conversion convention, effective dose per unit exposure at work is 1.1 millisievert per millijoule hour per cubic meter. Regarding action level in drinks, radon concentration should be set at 200 to 600 becquerel per cubic meter. If we calculate the dose using these radon concentrations, annual effective dose was estimated to be 3 to 10 millisievert per year. Action levels in workplaces, radon concentration is 500 to 1,500 becquerel per cubic meter. The corresponding annual effective dose was calculated to be 3 to 10 millisievert per year. Occupation annual limit on exposure is 14 millijoule per hour per year, averaged over 5 years. 35 millijoule hour per cubic meter in a single year. Here is an occupational annual limit in terms of radon exposure. ICRP publication 115, Lung Cancer Risk from Radon and Progeny and Statement on Radon. In 2010, ICRP publication 115 updated estimates of the risk of lung cancer associated with exposure to radon and its progeny. This was based on epidemiological results from cohort of miners exposed to low levels of radon and for the first time from studies of lung cancer risk associated to indoor radon. Publication 115 proposed a nominal risk of 5 times 10 to the minus 4 per working level month, replacing ICRP publication 65 value of 2.83 times 10 to minus 4 per working level month. In the statement of radon, the Commission reduced the upper reference level for homes was from 600 becquerel per cubic meter to 300 becquerel per cubic meter. The statement recommended 1,000 becquerel per cubic meter as the entry point for applying occupational radiological protection requirements in existing exposure situations. ICRP publication 126, Radiological Protection Against Radon Exposure. In 2014, recommendations on radon were updated, considering the key scientific findings of ICRP publication 115 and the most recent ICRP principles and methodology. Actually, namely ICRP Publication 103, the 2007 recommendations of the International Commission on Radiological Protection. An integrated approach for protection against radon exposure in all buildings is recommended. Whatever the purpose of the building, and regardless of whether the occupants are at work or not, the same reference level should be applied and protection be optimized in all circumstances. These recommendations confirmed that authorities should set a national reference level as low as reasonably achievable in the range of 100 to 300 becquerel per cubic meter. Radon concentrations are compared to the reference level to help control radon in homes and most workplaces. ICRP Publication 126 recommended a specific graded approach for workplaces for applying occupational protection requirements, where workers' exposure to radon is not considered as occupational, namely office buildings. The first step, reduce the concentration of radon to a level that is as low as reasonably achievable below the same derived reference level as set for dwellings. The corresponding annual dose is usually lower than that in dwellings because the time spent in workplaces is usually less than the time spent at home. If difficulties are met in the first step, a more realistic approach is recommended as a second step. Second step, optimize protection using the actual parameters of the exposure situation, such as occupancy together with a reference level of the order of 10 millisievert annual effective dose. Despite all reasonable efforts to reduce radon exposure in workplaces, if the exposure persists above the reference level expressed in effective dose, the workers should be considered as occupationally exposed. In such cases, relevant requirements for occupational exposure should be applied. For some types of workplaces, national authorities may decide that exposure of workers to radon should be considered occupational regardless of whether concentrations are above or below a reference level, because the workers are inevitably and substantially exposed to radon, and their exposure to radon is more intimately or obviously related to their work activities. Authorities should consider establishing a national list of such workplaces or work activities, namely mines and other underground workplaces, thermal spas. Regardless of whether workers are considered occupationally exposed, effective doses should be kept below the upper value of the range of for existing exposure situations to 20 millisievert per year. Here's the general approach for the management of radon exposure. Building or location. In the case of drinks, here is a derived reference level, DRL, between 100 and 300 becquerel per cubic meter. In a few cases at workplaces, such as underground mines, summer spas, it should be considered occupational exposure. In this case, we have to take optimization and we have to take a limit optionally. The measurement, if the derived reference levels, the concentration, if the radon concentration below DRL, based on the ARARA, it will be okay. If the radon concentration is above derived reference level, based on the ARARA, we have to make measurements. In the case of workplaces, measurement, if the radon concentration is below derived reference level, based on the ARARA, it will be okay. But if the radon concentration is above the derived reference level, we have to make a realistic approach based on the ARARA. If the annual dose is below 10 millisievert per year, we go back to the ARARA, and if not, we have to consider the occupational exposure. We have to take optimization and limits, annual limits, optionally. ARARA is as well as reasonably achievable, taking economic and societal circumstances into account. ICRP publication 137. Occupational intakes of radionuclides, Part 3. Although protection against radon is primarily based on measurement and control of levels of exposure, those estimates are required in certain situations for workers. Those estimates are of value for protection purposes when workers are exposed to more than one source of radiation, as is the case for underground miners. In addition, those estimates are required for comparing sources of public exposure. Using the nominal risk coefficient from ICRP publication 115, 1.4 times 10 to the minus 4 per millijoule hour per cubic meter. And ICRP publication 103 determinant values are those conversion convention value of 3.3 millisievert per millijoule hour per cubic meter for adults is obtained. This is fundamentally based on epidemiological evidence. On the other hand, using the dosimetric models, the dose coefficient are 3.3 per millijoule hour per cubic meter for workers in mines and 4 millisievert per millijoule hour per cubic meter for sedentary office workers. Using the same methodology, the dose coefficient for exposure in homes is 3.7 millisievert per millijoule hour per cubic meter. For tourist caves and indoor workplaces where workers are assumed to spend 2/3 of time in exercise, the dose coefficient are 6.7 and 5.7 millisievert per millijoule hour per cubic meter, respectively. There is remarkable consistency between coefficients obtained by dosimetric calculations and conversion coefficient based on epidemiological comparisons. Taking account of both methods and their associated uncertainties, the following rounded dose coefficient present in ICRP publication 137 are recommended. That is to say, for building and underground mines, in most circumstances, the recommended dose coefficient is 3 millisievert per millijoule hour per cubic meter. Approximately 10 millisievert per working relevance. The corresponding dose coefficient expressed in terms of radon-222 gas exposure depends on the equilibrium factor between radon gas and its progeny. Using the standard assumptions of equilibrium factor of 0.4 for most indoor situations, this dose coefficient corresponds to 6.7 times 10 to minus 6 millisievert per becquerel hour per cubic meter. While ICRP publication 137 does not specifically address public exposures, it is intended that this same dose coefficient applies to exposures in homes. Dose coefficient for radionuclide intakes by members of the public will be published in due course and will include radon. Using this dose coefficient, exposure to radon at the upper value of the national reference level of 300 becquerel per cubic meter recommended in ICRP publication 126 correspond to an annual effective dose of 4 millisievert at work and 14 millisievert at home. For the specific situations of indoor work involving substantial physical activity and exposure in tourist caves, the recommended dose coefficient is 6 millisievert per millijoule hour per cubic meter, approximately 20 millisievert per working level month. In cases where aerosol characteristics are significantly different from typical conditions, where sufficient reliable aerosol data are available, and estimated dose warrant more detailed consideration, it is possible to calculate site-specific dose coefficient using data provided in ICRP publication 137. Here is a flowchart of effective dose due to inhalation of radon. First, we obtained annual radon concentration in becquerel per cubic meter. Using the proper equilibrium factor, typical value is 0.4, we can obtain the annual equilibrium equivalent radon concentrations in Becquerel per cubic meter. By multiplying the occupancy factors, namely 7,000 hours per year indoors, we will get the time integrated equilibrium equivalent radon concentrations, Becquerel per cubic meter hour. Then, when the dose conversion factor is assigned, we can obtain the annual effective dose in millisievert per year. Dose conversion factor is affected by particle size of radon progeny, biological parameters, and etc. For dose assessment, equilibrium factor depends on the ventilation rate of the houses, indoor air quality, activities of residents, and so on. Dose conversion factor includes the following process and condition: deposition of radon progeny aerosols in the respiratory tract. The particle size is a dominant parameter. Absorption, lung to blood. Biokinetics. Dose calculation with radiation weighting factor, tissue weighting factor, and assigning partition for tissue weighting factor among thoracic region, capital BB, BB, and AI. Here are challenges in lung dosimetry of radon progeny result from non-uniformity of radon progeny deposition within the bronchial region and among bronchial airway surfaces. Short range of alpha particles in relation to the non-uniform distribution of sensitive target cells in bronchial epithelium. Relationship between stopping power and alpha particle range. The lung dosimetry model comprises 5 submodels: morphometric lung model, detailing anatomical structure of the lung in terms of the number of airway generations and their characteristics such as diameter, length, branching, and gravity angles. Second, respiratory physiology model defines the breathing patterns related to different physical activities. Particle deposition model comprises extrathoracic, bronchial, and pulmonary deposition efficiencies, physical deposition mechanisms in cylindrical airways, and related analytical deposition equation for specific flow patterns. Bronchial clearance model comprises mucocerebral mucociliary clearance and transport into the blood. The geometric model specifies the geometry of alpha particle interactions with sensitive target cells at different depths in bronchial epithelium. There are models currently used. Models where the absorbed dose to sensitive target cells in bronchial airway generations is calculated, such as deterministic and stochastic airway generation models. They are sometimes called anatomical or biological models. Semi-empirical compartment models, such as ICRP human respiratory tract model, combine many airway generations into components to simplify those calculations. They are sometimes called pharmacokinetic or biokinetic models. What is airway generation model? Lung is made up of airways co-generation. Trachea is regeneration zero. This is a straight duct with ring structure. Here. Generation zero. The upper bronchial consists of generations 1 to 16. 1 to 16. This is a series of branching smooth tube. Alveoli start appearing at generation 17. Airways are much smaller than the wall with alveoli is no longer smooth, as you can see, like this. Human respiratory tract is composed of three functional regions: extrathoracic region, nose, mouth, and pharynx. A filter to protect the lung. Tracheobronchial region, capital BB and BB. Bronchial and bronchiolar airways to distribute inhaled air to the gas exchange region. Alveoli interstitial region. Gas exchange between lung and blood takes place via alveoli. Inhaled radon and radon progeny may be transferred to the other organs of human body via the bloodstream. This is a schematic model of location of sensitive target cells, basal and secretory cells throughout the bronchial epithelium in capital BB region. Sensitive target cells in bronchial epithelium are defined as the cells receiving energy from radiation that lead to development of lung cancer. The range of 6 MeV alpha particle from polonium-218 fluid of a tissue is 48 micron, and that for 7.7 MeV, alpha particle of polonium-214 is 71 microns. Target cells, basal cells, and secretory cells. There are personal parameters affecting lung dosimetry. The most important personal factors are extrathoracic, namely nasal and oral geometry, anatomical structure and linear airway dimensions of lung, physical activities, and related breathing parameters, bronchial clearance velocities, spatial distribution and frequency of sensitive target cells in bronchial epithelium, human subject age, and smoking status. On the other hand, the most important environmental factors are attached and unattached particle size distributions, attached and unattached fractions, radon progeny activity concentrations, and their nuclide-specific distributions. There is a difference between ICRP model and airway generation model. While the ICRP model can be applied to the inhalation of any radionuclide, the generation-based models were specifically developed for inhaled radon progeny. The differences are the lung structure consists of only three components: the large bronchial airways, capital BB, the smaller bronchial airways, BB, and alveolar interstitial region, AI. Deposition fractions in tracheobronchial, TB, and AI components are obtained by appropriate fits to human experimental data and expressed as functions of particle and flow parameters. It is a semi-empirical. The clearance pathways and related half times refer to the whole component and not to single airway generations. Doses to bronchial target cells are computed for the total alpha activity in a given compartment rather than for steady-state surface activities in individual cylindrical airway generations. Here is a comparison of radon progeny. Absorb those coefficients in bronchial, capital BB, bronchiolar, and alveolar interstitial airways by three lung dosimetry models. The region and mode, unattached mode, attached mode. Here the computer mode calculation code to determine radon progeny dose, absorbed dose per working relevance. There are three types of calculation codes. RADP IMBA is ICRP Human Respiratory Tract Model, Deterministic Regional Compartment Model. RADOS, Deterministic Airway Generation Model. Ideal dose, Stochastic Airway Generation Model. The comparison, here is the comparison of the lung cancer risk per unit exposure based on dosimetric and epidemiological approaches. Here is the exposure expressed in working relevance. Using the lung model parameters and aerosol parameters, we will obtain the absorbed lung dose. Then, considering radiation weighting factor, tissue weighting factor, and assigning partition for tissue weighting factor among thoracic region, we will get the effective dose. Then, with the determined adjusted nominal risk efficient, we will obtain the risk. This flow represents a dosimetric approach. On the right side, after getting the exposure values using the risk model, we just get a risk based on the epidemiology. This is the epidemiological approaches. Tissue weighting factors and respiratory tract regions. Functional regions of human respiratory tract model. Extrathoracic region included in remaining tissues 0.12 as a totally 14 tissues. The corresponding value is quite small at the extrathoracic region. Tracheobronchial region, namely bronchial and bronchiolar airways and alveoli interstitial region, the tissue weighting factor of 0.12 for lung is equally divided into three regions, 0.333, 0.333, and 0.333. This figure shows a regional deposition as a function particle size calculated with a human respiratory tract model for a standard worker. Blue continuous line, bronchial region, continuous line, bronchiolar region, dash line, half extrathoracic equals half of the deposition of extrathoracic region. Approximating the deposition during the inhalation phase. Filtration in the ET region affects the fraction of particles entering the lung. This region can play a role of filtration of radon progeny aerosols. In this figure, unit density and unit shape factor were assumed. Here is a particle size, particle diameter in nanometer, and regional deposition. As you see, unattached mode around here, unattached mode, here's a nucleation mode. This is a accumulation mode. Then here is the coarse mode. I summarized those conversion factors in ICRP publications. This is ICRP publication 50, 1987. 6.4 indoors, 8.9 outdoors. The unit is milliworking level, millisievert per working level mass. In 1993, from publication, ICRP publication 65, 5 at work, 4 at home. 1994, according to ICRP publication 66, based on the human respiratory tract model, this calculation provides 13.4 millisievert per working level mass at work. Just 1 year after, there was a large difference between the two. Here, this is the epidemiological approach, and here is a dosimetric approach. 2000, using ICRP publication 66 model, they calculated the dose conversion factor with 15 millisievert per working level months at home. There are 3 times difference between the two approaches. Then 2001, my colleague, they calculated dose conversion factor using ICRP publication 66 model, 13.7 at work, 14.3 at home. After 9 years, ICRP publication of 115 gave new value based on the epidemiological data. 9 millisievert at work, 7 millisievert per working level month at home. In 2014, ICRP publication 126, 12 millisievert per working level month at work, 9 millisievert per working level month at home. The most latest publication, ICRP publication 137, based on the dosimetric approach, this publication gave us 10 millisievert per working level month at work. These are very similar each other. Maybe I have to finish lecture today. Hello?
Hello.
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 Yes. I will stop here and I will continue tomorrow.
So we'll be meeting Dr. Tokonami tomorrow morning at Indian Standard Time 10 a.m. Like today we started.
Yep. Yes.
So thank you very much, Professor Tokonami, sir, for sharing your expertise and perspectives for enriching our understanding of dosimetry of radon and its isotopes. If participants have any questions, then they may ask. So dear participants, if you have any question, please unmute yourself.
I have one particular question, Dr. Tokonami. Like these models which you were discussing, the dose conversion factors which you have calculated, means how they are different from the hair compartment model and Bernard's model. Means
Okay.
tissue equivalent factors are different, rather used in these models, or they are the similar one?
It's a similar.
They are the similar one.
Yeah. But depending on the default value.
Okay.
Yeah.
So anyone from the audience? Abhishek, if you have any question?
No, so thank you very much, sir.
So then we can thank the speaker and we will start our next session at around 2:30. So thank you, Dr. Tokonami, for giving your valuable time. So we will see you tomorrow. Thank
See
you.
you tomorrow.
Thank you.
Thank you very much.
Thank you.
So dear participants, we can have a break of 5 to 10 minutes and we will meet at 2:30 for our next lecture.
Thank you. Sure. So we will be meeting for the next lecture at 2:30. Just 5 to 10 minutes break is there. So after this break, we will be starting the final session of this day. So I will be joining it around 2:30.
Okay, sir.